Hello, thank you for joining me for a new chapter of Year 13 Maths for Edexcel. So it's the Stats and Mechanics portion of the course, in particular it's for statistics. It's chapter 1.1, which covers regression, correlation and hypothesis testing. So it's a mix of the old and the new. Some of this will seem very familiar, bits of it will be, of course, new, with it being Year 13 rather than Year 12. So we're going to start today by having a look at exponential models and coding exponentials as linear relationships, which we saw in chapter 14 of the Pure Book for year 12. So it'll be partly revision, partly something new. So I'll recap what was covered in year 12 just to get you back up to speed, and then have a look at some worked examples on the uses of coding exponentials as linear relationships. We'll also touch on mentioning about regression lines, but the equations of a regression line we'll do next lesson, not this one today. Anyhow, let's get straight on and get warmed up. I've picked 4 questions for you here, so partly adapted from actual A-level questions, some I've just made myself. So 1, 2, 3 and 4. Write them out if you've not got a copy of the notes in front of you. Pause the video now and have a go at them, and when you're ready to see the solutions and check yours against my own, press play and then I'll guide you through the answers to them. Alright then, so let's have a look together at question number 1. So number 1, a bit of a trick here, a bit of a tip. It says use the laws of logs, solve this equation here. So we've got log of one thing minus log of the other. Using the laws of logs, you should hopefully remember you've got log of one thing minus log to the same base as something else. It's the same as the log of that thing divided by that thing. So I can put this into a fraction. So all of this here can just be rewritten in terms of a single logarithm. So this is in terms of log base 5. This is just an ordinary number. So I can't really compare easily a logarithm with a number. It's comparing different things. So what I could do here is I could rewrite 2 in terms of something to log base 5. Remember, the log of a number is the power that a number needs to be raised to get this answer. So what power, sorry, I'll start this again. Simply put, 5 to the power 2 is 25. So log base 5 of 25 is 2, because I'd need to do 5 squared to get 25. So what we can do here is just replace the 2 with log base 5 of 25. So now one side's equal to the other. They're both in terms of log base 5. So what we can say for definite is that this thing here must therefore be equal to that thing there. So essentially we can get rid of the logs and just realise that 3x minus 1 over 2x minus 1 must be equal to 25. So now I've unravelled the logs, it just becomes a GCSE question essentially. So now we can just rearrange and solve. So 3x minus 1 equals 25 multiplied by 2x minus 1. Expand this side. 25 times 2x gives 50x. 25 times minus 1 is minus 25. If I subtract 3x from both sides, this side will become 47x. 3x take 3x will vanish over here. Then if I add 25 to both sides, that'll cancel this minus 25 over here. Minus 1 plus 25 gives 24. Therefore, dividing both sides by 47, x is going to be 24 over 47. And we've solved it. So we're off and running. That's the first question done. Let's do another. Question 2. By taking logs, solve the equation 3 to the power 2p minus 1 equals 4 to the power 250. Give your answer to 1 decimal place. I've picked these values so you can't easily do it on your class whiz. You have to trust in terms of knowing your laws of logs well enough. So again, like it says, take logs of both sides. So the log of 3 to the power 2p minus 1 must equal the log of 4 to the power 250. Now, remembering the laws of logs, if we're taking the log of something which is raised to a power, we can drop the powers to the front. So 2p minus 1 we can drop to the front. So 2p minus 1 times by log 3 equals 250 multiplied by log 4, because both the 2p minus 1 power can go here, and 250 can drop down to the front of this logarithm 2. So, if we divide both sides by, for example, log 3, that will just leave us with 2p minus 1 on the left-hand side, which isn't a bad thing to have. So 2p minus 1 equals 250. That equal sign's a bit wonky. Whoops. Sorry, that'll bug me. Just looks a bit rubbish there. So 250 log 4 divide by log 3, and I can work out what this is. Okay, so 250 log 4 divided by log 3. So log just means log base 10. You could do log to any base as long as the log of this base is the same as the log of this base down here. So dividing that by log base 10 of 3 gives me 315.464, and so on and so on. Next, if I add 1 to both sides, 2p will be 316.464. Finally, divide by 2. P will be 316.464, and so on and so on, divided by 2. Let's see what this gives us. So here we needed to add 1, then divide by 2, and we're given the answer to 1 decimal place, like the question asked. 158.2 is what P is, at least to 1 decimal place anyway. Warm up question 3. We've got a discrete random variable, big X, with the following probability function. So probability that the particular variable takes a specific value, little x, equals the following. It's only defined for x, little x being 2, 3 or 4, and 0 probability elsewhere. We have to show that k equals 1/40th. So what we can do here is create a table of values. So we need to do what x is, and the probability that big X takes on that particular value for each particular one. So x, little x, is only defined for this discrete random variable for 2, 3 and 4. It's 0 elsewhere. So we just think of 2, 3 and 4. And the probability of it actually taking that particular value next. So when little x is 2, the probability of the distribution taking that exact value is going to be k multiplied by this thing here. So we can work this out. We just sub in when x is 2. So it's going to be k times 2 times 2 squared, which we can work out. So 2 times 2 squared, because x is 2, minus 6. That gives us a value of 2. So that's k times 2. In other words, 2k. Then when x is 3, that's going to have a probability of it being 3 of k times, in brackets, 2 times 3 squared minus 6. So 2 times 3 squared minus 6 gives us 12. In other words, k times 12, that's going to be 12k. Then the probability of big X taking a specific value of 4 is k times 2 times 4 squared minus 6. So working out the brackets here, subbing in when little x is 4, 2 times 4 squared minus 6, that gives us 26. So when x is 4, the probability of big X taking that value is 26k. Now ultimately goes back to GCSE. So the sum of all probabilities of all the possible outcomes for any event totals 1. So therefore we can say 2k plus 12k plus 26k must total to exactly 1 whole unit. 2 plus 12 is 14, so that's 14k, plus 26k, that's 40k. So 40k is 1. Divide through by 40, we see that k must indeed be 1/40th, like we wanted to prove all along. So that's part A done. K is a 40th, like we wanted to show. Part B says to find the probability distribution of X. That's essentially just using what we've worked out for part A. So we're just going to use, so I can just actually just copy this really and cheat in a way. So for B, we're just going to sub in what K actually is, and we've got our actual numerical distribution. So for part B, the probability of big X being 2 is 2k, but because k is 1/40th, this is going to be 2/40ths. You can simplify it down if you want to, but because it's probability, you don't have to. So that just becomes 2 over 40. 12k becomes 12 times 1 over 40, which is 12/40ths. And of course 26k just becomes 26/40ths. And then we're done. As a double check, do those fractions, 3 of them added together, add up to 1? Of course, yes they do. 40 over 40, which is 1. So that's question 3 done. One more, warm-up question 4. And finally on the warm-up question 4. So we have Ed and Pete playing each other at GoldenEye, and for each match, independently of all others, the probability that Pete loses is 0.4. Find the probability that in 10 games, Pete loses exactly 3 other games. So here we can hopefully deduce that it's either a win or lose game. So Pete's either going to lose or not lose. Also as well, each match is independent of all others. So each match is independent and it's either a win or not win, or lose or not lose. So essentially we can model it as a binomial distribution. So X is going to be binomial distributed. We've got 10 games, and the probability of him losing just 1 game is 0.4. So the parameters are 10 for 10 games and 0.4 the probability that he loses any 1 game. So first of all, the chance that he loses exactly 3 other games. So we want to find for part A the probability that X takes on the value of exactly 3. What's the probability of him losing exactly 3 games? So on the calculator, what we can do here is get into the right mode. So I'll just explain how to do this. We press menu, and then we scroll to option number 7 for distribution. And because we want to find an exact probability, X equal to 3, we choose binomial PD. Press 2. Now we type in the parameters. So X is 3 because we're interested in working out him losing 3 out of a total of n being 10 games, and the probability of him losing just 1 is 0.4. So that's what we type in, press equals, and the calculator will do the legwork for us. So the probability to 3 significant figures is 0.2149. So 0.215 is what we'd round about 4.2. So 0.215. Next, for part B, slightly different question. Now we want to work out the probability he wins more than 3 games. So for B, we want the probability that he wins more than 3, so the chance that the distribution takes on a value greater than 3. That's the same as all probabilities, apart from the probability that he loses 3 or fewer games. So I keep saying win, I mean lose. He's losing the games. So the probability of him losing more than 3 is 1 minus probability that he loses 3 or less. Here, because the distribution we're trying to find now is based off an inequality, we need to use binomial CD, which I'll show you how to do now. So again, we get the calculator ready. This time though, we press menu 7. Now we scroll down to get to binomial CD. So now we press option 1. And now what we're wanting is 3, 10, 0.4. Because this is now the cumulative distribution though. This isn't working out the probability of him losing exactly 3 games. This is a cumulative probability of him losing 0 or 1 or 2 or 3 games inclusive. So press equals. The chance of him losing 3, 2, 1 or 0 games is 0.382, correct to 3 significant figures. So we do 1 minus 0.382, and if we calculate that, that gives us a probability of 0.618. So he's got about a 62% chance that he'll win more than 3, that he'll lose more than 3 games. So that's question 4 completed. Now the main body of the lesson. So what we're talking about here today is coding exponential models into linear relationships. So what does this mean and why would we do it? So I'm just going to explain here in these next couple of slides. So at year 12, we looked at how exponential models can be transformed into linear functions by using a change of variables. And we did this in the pure maths course, the chapter Exponentials and Logs. That was chapter 14.8. So let's first revisit the 2 main ways in which we can code exponentials into linear relationships. So one common exponential model is y equals ab to the power x. So how to get this into the form y equals mx plus c? And y equals mx plus c is, of course, as you know, the general equation of any straight line. So what we can do here is rewrite y equals ab to the power x and take logs of both sides. So if we take logs of both sides of this equation, we have log of y will equal the log of ab to the x. So this means log a multiplied by b to the x. It's log of all of that. It's a log of a product, where the product was a multiplied by b to the x. By the laws of logs, this can be split into log a plus log of b to the power x. And if we're taking log of something with a exponent, that exponent can come down to the front, and so we can go further and say this is the same as log a plus x log b. So next what I want to do is rearrange this and just compare it to the general form of a straight line. So therefore we can say that log of y equals x times log b, which I'm going to rewrite slightly. I'm going to rewrite log b first, times x plus log a. And so because y is a variable, the log of y will be a variable as well. So this is a variable, just as y is. Log of b, b is a constant. So because b is a constant, the log of b will be a constant. So log of b relates to m. X is a variable, as is big X. And finally, the log of a is a constant, as is c. So just coding it as y equals mx plus c. The coding we can use here to get this exponential equation into a straight line is as follows. So the coding is we let y, big Y, equal log of y, and big X is just equal to x. So we don't really need to change what type of variable x is. We can change its letter, but we don't need to transform it in any way beyond that. The second case is if it's an exponential of this form, where we've got y equals some constant multiplied by x to some constant power. So again, we can take logs of both sides here. So if I write y equals ax to the n, and take logs of both sides once again, this time we'll get log of y equals the log of ax to the n, which is again the log of a product of two things. So I can split this into log a plus the log of x to the power n. So log of a, I can keep as log of a, and because this is the log of something to a power, that power can drop down to the front using the laws of logs, so that can become n log x. So therefore, just rewriting this in a slightly rearranged form, we can see that therefore the log of y equals n times log x. So I'll just write this as n times log x plus the log of a. So again, just comparing different parts. Big Y relates to the log of y. Both these are variables. M, the gradient, which is a constant, will relate to this n. So the gradient will be the n. Big X we can code to be the log of x. And finally, the y-axis intercept for this straight line relationship, for positive c, relates to plus log a. So again, the coding for this one is just as follows. So like I've said, we can code big Y as log Y, and this time big X becomes log of X. So the difference here mainly is in the first one, we just have to code Y into a logarithmic function, but we can leave the X alone essentially, whereas here we code both variables, the original small y and the small x, both into logarithmic variables. That's the key difference between these two. If you forget them, always remember you can derive these from first principles, just like I have here, if you're not sure of if it's of a form y equals ab to the x, or of a form y equals ax to the n. Take logs, and these can be fairly easily derived yourself, rather than having to remember too much and increasing that cognitive load of yours beyond what it needs to be. So that's all well and good, but why would we bother doing this in the first place? Well, the benefit of coding a non-linear relationship into a linear one is because linear relationships are easier to analyse and interpret. They're just, simply put, they're easier to get your head around. For instance, experimental data will often not demonstrate a linear relationship at all. It can be quite hard to see if there's a pattern, if any. So because an experiment might not show a linear relationship, that's not to say that there's necessarily no relationship at all. There might well be a relationship. For example, the data may well fit, for example, an exponential model, which is what we're going to be looking at today. In addition to that, to see if the data fits an exponential model, rather than trying to get your head around a really awkward exponential equation involving powers of e, it's just much easier to use coding and logs to transform an awkward exponential model into a good old-fashioned GCSE-style linear relationship. Then, if the coded data fits a linear model, we can therefore deduce that the original data must have indeed fit an exponential model. To see how well the transformed data fits a straight line, we could still manually draw on a line of best fit by eye, just to see how strongly the data points are correlated, like you would do at GCSE. Get your ruler out and just sort of see where the line would go. You can still get a good feel for if it's well correlated or not. However, at GCSE we can be more technical. Sorry, at A level we can be more technical. For A level we can compute correlation and the line of best fit exactly using formulae, or to be more practical and easier for yourselves, we can use the calculator. However, we're not going to do that today. The exact calculated line of best fit for linear data is called a regression line. So a regression line essentially is a fancy word for a line of best fit that's been calculated exactly. And like I say, we're not going to do that today. I'll show you how to do that next section. Let's have a look at a couple of worked examples then. So worked example 1. We've got a table of values showing some data collected on the temperature in degrees C of a colony of bacteria T and its growth rate G. It's got temperatures going along here in degrees and the growth rate of this colony of bacteria. So this looks to be not a linear relationship right now. So it's going up by 0.4, then 0.3, then goes up by about 0.7 there. So it's not seeming to be linear. So what we can see here is if it's can be coded. So the data is then coded using this change of variable where x is the same as t and we code y as log of g. The regression line of y on x is found to be y equals minus 0.2215 plus 0.0792x. So part A, Mika's saying that this constant of minus 0.2215 shows that the formula means a colony is shrinking when the temperature is 0. First of all, we need to explain why Mika's wrong. So for part A, when the temperature is 0 and temperature is T, and T is 0, because x is T, then we can say that x is 0. So if we sub in when x is 0 into this, what we'd get is y equals minus 0.2215. But of course, y itself is coded to be the log of the growth rate g. So because when t is 0, x is 0, this bit here vanishes and we just get y equals minus 0.2215, we can then put this back in terms of g. So therefore, the log of g is minus 0.2215. So next we need to recall if a variable is coded in terms of a log and we're not told the base of a log, we have to assume this is log base 10. To undo the log of g, what we can do is state that therefore g is going to be 10 to the power of minus 0.2215. I'll remind you of why this is the case. So for example, if we had the log base 10 of 100, that means that what power of 10 do we need to raise 10 to get 100? That would be 2. Okay? And therefore we can switch this around, so we could say that 100 equals 10 squared, which of course is true. So essentially logs and powers for 10, for 100 and 2 switch around like so. And so g, what we're taking the log of, is the base, which again is 10, to the power of what the answer was, which in our case was minus 0.2215. So if we just calculate this, 10 to the power minus 0.2215, and see what we get, we can then work out if Mika's right, and we get a negative growth rate. So let's try that. So 10 to the power of minus 0.2215, that gives us 0.600, two 3 significant figures at least. But ultimately, this isn't a negative growth rate. If a colony was shrinking, g would be minus to indicate that the colony isn't growing, it's reducing. 0.6 isn't huge, but ultimately it's greater than 0. So therefore, Mika is wrong. Not Mike. Sorry, I'm thinking of a Mike there. Mika is wrong because 0.6 is a positive growth rate. So we just need to write something along these lines to get the credit in an exam or an assessment. For part B, We're told that the data can be modelled using an equation of this form: g equals k times b to the power t, where k and b are some constants to be found. And of course we need to find the values of k and b. I'm going to show you two ways of doing this. The first way is my preferred way. So let's have a look at this first of all. So method A. So what we could do here is start with a model we want to show it fits, which is g equals kb to the t, and manipulate it. So g equals kb to the t. Then we can take logs of both sides. So the log of g will equal the log of kb to the t. Just doing the same to both sides of the equation. Now we can decompose this log, because this is the log of a product. So this is the same as log of k plus the log of b to the t, which becomes log k, and of course this power drops down to the front, so we can say that's t log b. So rearranging this and comparing it to this form here, we can therefore clearly see that, so log g equals, put the constant thing first, because this constant thing is first in this equation. The constant here is k. K is a constant, so the log of k will also be a constant. Again, I can't seem to write for toffee today. I must be quite tired. I apologise. Log of k, I was going to write loc, which clearly is wrong, plus log b multiplied by t. If I now write this underneath, we can compare and contrast what we have here, and then we can work out and deduce what relates to what. So y equals minus 0.2215 plus 0.0792x. So as we can see, log of g relates to y, log of k must relate to this constant here, the log of b, wrong colour, must therefore relate to the positive 0.0792, and like the question says itself, t relates to x because it was coded as so. X is t, t is x. So now we can work out what k is and what b is separately. So log of k is minus 0.2215. In fact, we did this earlier for part A. So we worked out from part A. If we look here, we took log of both sides, and we got that k was 0.600. Well, we know that because to get k, we'd have to do the same as what we did earlier. We'd have to do 10 to the power of minus 0.2215 to undo this log, to do the anti-log. If you're slightly older than, some teachers. Used to call anti-logs powers. So k is 10 to the power minus 0.2215, which is 0.600. As well as that, b, log of b, sorry, it must be 0.0792. Log of b, rather. So therefore b must be equal to 10 to the power of 0.0792, which again we can calculate. So 10 to the power 0.0792 gives us a value of 1.20. So therefore, for part B, we can say that k equals 0.600, b equals 1.20. So therefore, g, the relationship we're after, is 0.600 multiplied by 1.20 to the power t. Ultimately, we just need to find what k and b are. So we need to find what k and b are. We have done that. K is 0.600 and b is 1.20. The textbook for Pearson uses a slightly different approach, which isn't my preferred approach, but if that way has bamboozled you, I'll show you the way that Pearson have used, which is method B. And I apologise if I ran slightly over. So another way of thinking this through would be to realise, because y is log g, I can just replace this y here with the log of g. So log g equals minus 0.2215 plus 0.0792x. So the log of g, to undo the log of g, I can do 10 to the power of g to get it in terms of just an exponential without having to think about the logs. So if I take this to the power 10, so we can say that g, oops, it's gone a bit wrong, g will be equal to 10 to the power of log of g, raising it to the power of 10, and then the power being a log, the power 10, powers of 10 and the log undoes each other, so we're just left with a g. So basically I'm raising both sides to the power of 10, so raise this all to the power of 10 would give me 10 to the power of minus 0.2215 plus 0.0792x. Now in the same way we can split this power into 2 bits. So because it's one thing plus another, you can say that's the same as 10 to the power minus 0.2215. Then using the laws of indices from GCSE, 10 to the power of a plus b is the same as 10 to the power of a multiplied by 10 to the power of the other thing. So it's going to be multiplied by 10 to the power of 0.0792x. But I'm going to partition this into just 10 to the power of something multiplied by that thing to the power of x, using the power idea from GCSE. So 10 to the power minus 0.2215. We could work that out again fresh, or we can just use what we had here. Trust me, that's 0.600. And 10 to the power 0.0792 gives 1.20x. So using this approach, we can then compare what we've got here for g against what g needs to be. So g equals k b to the power t. So obviously and quite clearly I'm hoping we can see in our case that the 0.600, in fact I'll use a different colour, my apologies. Let's go for a orange. So 0.600 like so. That's going to relate to k. Like we said, k is 0.600. Then multiplied by b to the power t. T is x, like we said here. So therefore b has to be 1.20, which again we mentioned before as well using this method A, which is my preferred method, but pick whichever method makes most sense to you. So that's worked example 1 done. Let's have a look at one more before I ask you to try some of these on your own. So worked example 2 is a scatter diagram based one. It shows a relationship between two sets of coded data which are related to each other. I've called these big X and big Y, which are plotted, and here this is coded data that's been plotted. So big X equals log of small x and big Y equals log of small y. the regression line, essentially the calculated line of best fit of y on x, is shown on the right. This is the regression line in bold black, and it passes through the points, it passes through the points 15, 25 and 65, 108. So what we need to do here, first of all, for part A, is to state whether this relationship between y and x is of the form y equals ax to the n, or if it's y equals an to the x. So this is what I mentioned earlier. You can deduce this yourself if it's y equals ax to the n or y equals an to the x. So I'll show you why it's of the form y equals ax to the n. So for part A, what we can show here is that if the original data type was a relation where it's y equals ax to the n, take logs of both sides, log y is log of ax to the n, which can then be split into log of a plus log of x to the n. That gives us log of a plus n lots of log x. And so by taking logs of both sides, the x is then tied up inside a log. So x is tied up in log of x, and y is tied up as log y. So y will be coded as log y, and then x is transformed into log of x, which is exactly what we're saying here. So in this case, what I've coloured in for y, log of little y is the same as y, log of little x is the same as big X. So therefore, it must be the type y equals ax to the n. Because by taking logs of both sides, we see that y becomes a log y and x becomes a log x. For part B, I'd like to determine the equation of this regression line here. Now this is very little more than Year 12 pure work. So we're given 2 points on this line. Again, going back to GCSE even, if we're told 2 points on a line, we can work out the gradient. So the gradient, we just do the change in y between these 2 points, divide by the change in x between these same 2 points. So the change in y is 108 minus 25, and the change in x is 65 minus 15. So if we just compute this to see what we get, so we've got 108 minus 25 on the top of the fraction, and we're dividing that by 65 minus 15 on the denominator, and that's going to give us a value of 1.66. So because this is of a form here, as we can see, it's going to be big Y equals mx plus c, where m is the gradient. We just worked out the gradient of this regression line. The gradient m is 1.66. Now to find out what the intercept is, this point here, what we can do is just substitute in a known point. So to find out what this value is here, the intercept, we can use either 15, 25 or 65, 108 and sub it into y equals mx plus c. So I'm going to choose 15 and 25 because these numbers are smaller, essentially. So let's sub big X is 15 when big Y is 25. So then y, big Y, 25 equals 1.66 times big X, 1.66 times 15 plus c. So therefore c will equal 25 minus 1.66 times 15, So let's see what that gives us. So 25 minus 1.66 times 15. That's going to give us a value of 0.1. So that value there, not drawn to scale, is going to be 0.1. So therefore, the regression line is going to be simply big Y equals 1.66 times big X plus the intercept of 0.1. Finally, for part C, we need to work out the value of A and the value of N, giving our answers correct to 3 decimal places where appropriate, in other words, where needed. So, for part C, we've deduced that it must be of the form y equals an to the x. So for part C, from y equals ax to the n, we got that log y equals log a plus n lots of log x. So log y. So I'm going to write this so I can compare with this equation here. So I've got a constant multiplied by a variable. So in our case, the constant is going to be n, and the variable is log x. So n times log x, then plus 0.1, which is a constant. So the constant thing on its own from this was just for log a. We can now compare and contrast this with what we had here when it was coded. So it's y equals 1.66 big X plus 0.1. So like we said, y is coded as big Y, where big Y is log of little y. So this one, what's wrong colour? Not doing very well in the colours today. So log of y relates to the big Y. N essentially is the gradient. So n, which is our m here, too many letters, I know what you're probably thinking, is 1.66. Big X, like it says, is coded as log of little x, and so this here relates to big X, and then log of a finally is going to be 0.1. So we can work out what n is. So we're told n, essentially n is just 1.66. We don't need to give this to 3 decimal places because we know exactly it's 1.66. So therefore n equals 1.66, so we can just write that in, that's the easiest one to find. And log of a is 0.1. So to undo the log of a, we can raise both sides to the power 10. So a will equal 10 to the power of log of a, which is 10 to the power of 0.1. Let's see what this gives us. So 10 raised to the power 0.1, that gives us to 3 decimal places, 1.259. And that's all we need to do. In terms of the actual relationship, if you wanted to put what it was, not that the question needs us to do this, we'd have that y, the original exponential model, this is not the coded one, would be a, which is 1.259, multiplied by n, which is 1.66, to the power of x. So that's what the uncoded data would have satisfied. So these can be quite awkward at first, but with practice, obviously with practice comes not perfect, but with practice comes good enough. So now it's over to you lots. So here are my suggested questions for you to try. So turn to page 3, exercise 1A in your year 2 stats and mechanics book. Try all of exercise 1A apart from question 4. I don't think question 4 is as powerful as questions 1, 2, 3, 5, 6, 7, 8. And try and do your best at those. You know the drill by now. If you get stuck, do consult me, and please do leave a comment in the comment section if you are stuck. I do read them, and I like to read them. So I hope you found this video useful. Please do like and subscribe, and I hope to hear from you all very soon indeed. So take care, and until next time, goodbye for now.